Hello and welcome to Shridevi Classes YouTube channel where we inculcate interest and confidence in engineering subjects. Today in our playlist Induction Motor, we will study the phenomena of crawling in induction motor and we will understand the cause of crawling is presence of 7th space harmonics in air gap MMF wave. We will understand action of this space harmonics as crawling and will find out various reasons which produce problem of crawling in induction motor, and we'll also study the solutions which one has to follow to avoid crawling in induction motor. Let's start. All induction motor have a working rotating magnetic field of constant magnitude and constant rotational velocity, and the velocity of rotating magnetic field in RPM is known as synchronous speed and it is given as 120 F over P. It depends upon supply frequency and number of pole in the machine, and the rotor of induction motor runs with a certain amount of slip with synchronous speed and with 3 to 6% slip depending upon motoring load requirement. Induction motor attain a speed very close to synchronous speed, but if the same induction motor run at a very slow speed which is 1/7 of normal synchronous speed running, which is 1/7 of normal running of synchronous speed, this slow speed running of induction motor is known as crawling. Now in this world, crawl means moving with low speed, and our motor will move with a struggling low speed during this problem of crawling. During crawling, the rotor of induction motor rotates at a speed 1/7 of synchronous speed and the rotating magnetic field rotate with synchronous speed. So the speed difference between rotating magnetic field and rotor produce a very high amount of slip which leads high amount of induced EMF and current in rotor and their reflection in stator current. So motor runs with very high stator and rotor current, and it also produce huge amount of noise and vibration during crawling conditions. Now one important fact is this crawling phenomena has no concern with time harmonics of applied voltage or current wave. We know when supply got non-sinusoidal behavior, it has time harmonics, and a double harmonics have a frequency component of 2 times of normal supply frequency, and with double frequency the synchronous speed which is proportional to frequency also get doubled, and in that condition a motor will run at a double speed conditions, and crawling here mean running at a very low speeds. And the reason of crawling is presence of non-sinusoidal behavior in air gap flux wave, and in between stator and rotor in the air gap the resultant air gap flux become non-sinusoidal and has harmonic component in it, and these harmonics are known as space harmonics or belt harmonics. In an induction motor, crawling is caused by presence of spatial harmonics in air gap flux wave. Normally when a three-phase space displaced balanced winding got three-phase balanced time displace excitation, it produces sinusoidal flux distribution in air gap space between stator and rotor. But if winding is not balanced and slot per pole per phase is not an integer figure, then that uneven distribution of stator winding turns may produce space harmonics in air gap flux. Similarly, a bad designed relationship between number of stator slot and number of rotor slots also generate non-sinusoidal characteristic in air gap flux, and many a times when two teeth portions of stator and rotor get aligned with each other, there is an reduction in air gap reluctance and increase in air gap flux, and similarly when slots of both stator and rotor coincide with each other, there is an increase of air gap reluctance and reduction in flux. So this increase and decrease of flux caused by rotor and stator slots and teeth positioning also produce tooth harmonics, and they also results in non-sinusoidal behavior of air gap flux wave and space harmonics in MMF wave, which may cause crawling. If we have a distributed short-paced and balanced three-phase space displaced winding and it is excited by a balanced three-phase time displaced excitation, then in between stator and rotor in the air gap space we will have a sinusoidal flux distribution which have a constant magnitude and a constant rotating nature, and at two pole positions the magnetic flux density is got a peak magnitude in one direction and another direction as represented by dark brown curves here in this spatial investigation, and it at both side of peak position peak magnitude gradually and slowly decrease its magnitude, and in between two pole in the interpolar region it got least magnitude as represented by these dark blue lines. But unfortunately, due to unevenness in winding design and other problems related with stator and rotor slots, the air gap flux wave won't be a pure sine wave. And in this such non-sinusoidal sine wave, at mid position of maximum flux density, there is a little dip in flux density magnitude, and the flux distribution is not a gentle smooth sinusoidal behavior, but it got certain non-sinusoidal irregularity at peak positions. Similarly, at zero cross positions, there is some non-sinusoidal behavior in flux wave distribution. But even though the air gap flux distribution is non-sinusoidal, but positive half cycle and negative half cycle got a symmetry. So in harmonic analysis of this space MMF wave, we won't have even harmonics and only odd harmonics are present. And since the winding is in delta configuration, so such delta configuration have a typical characteristic which make triple harmonic MMF flux distribution as zero sequence component, and the sum of those triple sequence MMF component becomes zero. So such triple harmonic space MMF will not produce any rotating magnetic effect. So in this non-sinusoidal MMF distribution, we would have only odd harmonics, and that too non-multiple of 3. If an induction motor is designed in a poor manner and in winding slot per pole per phase is non-integer, and in the design number of stator slot and number of rotor slots got a adverse numbering and difference, and also the profile of slot and teeth is such that two adjacent slots produce a low reluctant position and two slots produce a high reluctant position in two nearby space positions, and will produce hooks and cusps of flux wave or increment and decrement in flux wave, and that results in this red diagram non-sinusoidal air gap flux wave in an adverse bad designed induction motor. And such non-sinusoidal flux can be considered as a fundamental sinusoidal flux distribution, which with peak magnitude in one direction represent one pole effect, and similarly peak magnitude in opposite direction produce another pole positioning. So if a fundamental flux MMF distribution produce two number of poles and there won't be even harmonics or triple and its multiple harmonics, then we would have 5th, 7th, 11th and 13th harmonic flux distribution. And in 5th harmonic flux distribution, every time when flux peak change its direction, the polarity of pole will also change. And in 5th harmonic, we will found that if fundamental frequency component of space wave produce two number of pole, the 5th harmonic will produce 10 number of pole, and similarly the 7th space harmonic of MMF wave will produce 7 times number of poles as compared to fundamental harmonic flux wave, as it is illustrated here. Each flux reversal create magnetic poles between two opposite directed flux spaces, and when the order of space harmonic is higher, the order of 7th harmonic 7 is higher than order of 5th harmonic. So when harmonic order is higher, the flux reversal number is also higher, so they represent higher number of poles. So 5th harmonic have 5 times number of poles as compared to fundamental, and 7th harmonic have 7 times of pole number. And rotating magnetic field of 3-phase winding have a synchronous rotating speed, and that speed is inverse of pole number. So we can say the synchronous speed of harmonic flux wave is obtained by dividing fundamental synchronous speed by order of harmonic. The fundamental flux wave revolves in air gap space synchronously at synchronous speed from leading phase to lagging phase with synchronous speed ns, and all harmonic flux also produce rotating magnetic field, and the speed of kth harmonic is 1 kth time that of fundamental magnetic flux synchronous speed. So 5th harmonic will have rotating speed ns by 5, where ns is rotating speed of fundamental space harmonics MMF wave, and similarly 7th space harmonic will produce rotating magnetic field speed ns by 7. Again ns is rotating speed of fundamental space MMF wave. If we study phase sequence, then we'll found that 5th space harmonic will have opposite phase sequence from fundamental MMF wave. So the rotating magnetic field of fifth harmonic will rotate in opposite to the direction of fundamental MMF wave, and the seventh harmonic space wave got similar phase sequence as that of fundamental MMF wave, and both fundamental and seventh rotate in the same direction but with difference of rotating speed. Fundamental got synchronous speed ns and seventh harmonic got rotating speed ns by 7, but both are in the same direction, and the fifth harmonic got opposite phase sequence, so its direction of rotation is opposite. Similarly, 5th, 11th and 7th space harmonic have opposite direction of rotation from fundamental magnetic flux, and 7th, 13th and 19th will have direction of rotation in the same direction as that of fundamental magnetic flux. Generally, in an induction motor, we can neglect torque produced by all higher order space harmonic MMF waves, and motoring torque can be consist of only three components. One is fundamental torque, which is produced by fundamental number of poles and it rotate with synchronous speed ns in one particular direction as per phase sequence. There is fifth harmonic torque produced by fifth space harmonic flux wave, which have 5 times number of poles as compared to fundamental pole number, so its synchronous speed is ns by 5, and as opposite phase sequence its direction of rotation is also opposite to direction of fundamental MMF rotation. Similarly, the seventh harmonic torque rotate with speed ns by 7 and its direction of rotation is in the direction of fundamental MMF wave. So we have three torque production in rotating machine: one fundamental having synchronous speed ns, another fifth harmonic having opposite direction of rotation and synchronous speed ns by 5, and third one is seventh harmonics with synchronous speed ns by 7 and direction of rotation in the direction of fundamental MMF wave. When a motor slowly accelerates and starts, the fifth space harmonic produce a braking torque between slip 1 and 2, and normally this small amount of braking torque can be neglected, and if we consider effect of seventh space harmonic, then that will produce torque in the same direction as that is produced by fundamental flux MMF, and this torque first increases, attain peak magnitude and then decreases to 0 when the synchronous speed of seventh harmonic 1/7 of original motor speed is attained, and after that if rotor accelerate, then in negative slip conditions it will act as a induction generator and produce reverse directed torque, and if seventh harmonic torque component overpower the driving torque of fundamental MMF, then the resultant torque behavior will have a black characteristic, and this resultant torque attain a peak magnitude and then got a negative torque speed characteristic for a certain reason, and in this negative torque speed relationship there exists a stable operating point, and if load torque match these motoring torque conditions, then a motor can rotate at 1/7 of synchronous speed, and that slow speed rotation is called as crawling. If we neglect small negative braking torque of fifth space harmonic MMF wave and add driving torque of seventh space harmonic MMF wave with fundamental MMF, then the resultant torque after attaining a peak show a dip in torque, and this is just like another negative torque speed characteristic, one which lies near synchronous speed of fundamental MMF, and this corresponding to synchronous speed of seventh harmonic, which is 1/7 of ns speed, and in this negative torque speed characteristic, if load torque on shaft after attaining certain speed match motoring torque here in this negative slope characteristic, and two torque line intersect each other, then at intersection point we will find a stable operating condition of motor, and motor will continuously run at constant speed without acceleration nearly at 1/7 of full speed, and this slow speed continuous operation of motor is known as crawling. When we start an induction motor with load, then motor produces a starting torque, and as speed increases load torque also increases, and in this negative sloped saddle region where torque decreases with increase of speed, if the two torque, motor torque and load torque, intersect each other, then we'll get a stable operating region, and a motor continuously rotate close to 1/7 of synchronous speed. Now this slow speed continuous rotation of motor in a stable mode is known as crawling. In induction motor operations, similar type of crawling may also exist at 1/13 of synchronous speed if 13th space harmonic also dominate in the same manner. And one significant thing is when motor slowly accelerate and load torque intersect motoring torque condition in this schedule section, then we'll got a stable operation conditions and motor stuck to characteristic position and continuously rotate without acceleration at 1/7 of synchronous speed in this negative sloped torque speed region, which is a stable operating region of motor characteristic. And this phenomena is known as crawling of motor. In crawling condition, rotor of motor rotate at 1/7 of synchronous speed and rotating magnetic field rotate at synchronous speed, and the difference of speed between rotating magnetic field and rotor speed produce a very high amount of slip, and due to high slip, rotor have high amount of induced EMF and induced current, and corresponding to that, stator also have high current, and such high current in stator and rotor produce high amount of copper losses, which generate heat and produce temperature rise to create damaging temperature conditions for the motor. And if this crawl condition continuously exists for a considerable duration, then it may damage our motor. In an induction motor, crawling can be avoided if we eliminate 5th and 7th space harmonic MMF waves in the resultant MMF distribution of motor, and this could be done by better design of winding with integer number of slot per pole per phase and optimum distribution of winding and short pitching of winding. And apart from that, we select optimum number of stator and rotor slots and avoid hoops and cups in MMF distribution. A good winding distribution and design involve proper short pitching of coil span. In place of full pitch, if we use short pitched coils, then it will reduce. We should use integral slot winding with slot per pole per phase as an integer number. With that, all poles of 3 phases become symmetrical to each other, and a balanced time displace excitation produce a sinusoidal air gaps MMF distribution, and avoid or eliminate 5th and 7th space harmonics in MMF wave. Skewing of rotor slots with stator slots reduce harmonics, and proper choice of number of slots in stator and number of slots in rotor also results in elimination of 5th and 7th harmonics. Proper optimum selection of stator and rotor slots is also explained here. A better optimum design of stator winding and number of slots in stator and rotor and the profile of stator and rotor teeth can generate a very good sinusoidal MMF distribution in air gap space and avoid all harmonics. For a good design, the number of slots in stator should be selected in such a way that they should give a integer number to slot per pole per phase. So slot per pole per phase, if taken as either 4 or 5, then it will also produce a better distribution of winding in slots, and good distribution and short pitching also reduce space harmonics. Now certain combination of stator slots and rotor slot can reduce 5th and 7th harmonics, and if 5th and 7th harmonics are reduced, then we won't have MMF which got 5 or 7 times number of poles than that of fundamental. The proper teeth profiles and number of slots in stator and rotor also reduce hooks and cuffs up and down in flux MMF in air gap space and avoid space harmonics. For a good design, number of slots in stator and number of slots in rotor should not be equal in number. The satisfactory results are obtained when rotor slots are 15 to 30% either larger or smaller than number of slots in stator. The difference of stator slot and rotor slot should not be 1, 2 or number of pole or 2 times of pole or pole plus 1 or pole plus 2. So for 4 pole design, if the difference of stator and rotor slots is either 3, 7, 9 or 10, then it will give a better sinusoidal MMF distribution and avoid harmonics MMF waves. And for 6 pole configuration, the number of slots in stator and rotor should have a difference of 3, 4, 9 or 10, so that we will have a better sinusoidal MMF distribution without harmonics and without problem of crawling. Another better design of induction motor is that we should have a higher amount of starting torque, so that torque at all speeds remain well above rated load torque, so that a fast acceleration will avoid crawling zone and shift motor torque speed characteristic to another negative slope schedule region and obtain a stable operating position where close to synchronous speed with 3 to 6% slip depending upon load torque requirement. So if a motor is well designed it will not experience crawling with normal power supply, or even when we use variable voltage and variable frequency drives with pulse width modulation techniques. But of course, if a motor is speed controlled with reduced voltage application, then at very reduced voltage conditions, there is a little risk of crawling conditions. One important thing is that crawling is not observed in slip ring induction motor, where we can improve starting torque by addition of extra resistance in rotor circuit, and that additional starting torque capabilities will fast accelerate motor and overcome this crawling saddle region and shift motor to final stable region very close to synchronous speed with small amount of slip. So crawling problem is not noticed in slip ring induction motors. It is a problem of only squirrel cage motor of small amount of starting torque, or motor started with reduced voltage type of starters. We hope this informative learning video has explained each and every conceptual learning about crawling in induction motor. We have explained role of space harmonics and problem associated with crawling, and also suggested measures to be adopted to avoid crawling in induction motor. For similar type of powerful conceptual learning on electrical engineering, do view our other videos. Thank you very much.